In this lesson, we are going to build a modern convolutional neural network from scratch, layer by layer. We will look at exactly how these mathematical blocks stack together to process complex image data. Complex AI models are constructed from a very limited set of specific repeating structural layers. Today, we are looking at the 5 core pieces: the fully connected layer, the activation layer, the convolutional layer, the pooling layer, and batch normalization. To get the most out of this, you should already be familiar with the multi-layer perceptron and how networks process 1D vectors of data. While AI moves at a rapid pace, these specific architectural blocks remain the most commonly used components today. Understanding how they operate gives you the direct foundation for modern computer vision. Let's start at the very end of the pipeline. In a neural network designed for classification, the last stop is usually the fully connected layer. Its job is to take the high-level features extracted by the rest of the network and make a final decision based on that knowledge. The mechanics here are straightforward. It performs a standard matrix multiplication, followed by an optional bias addition. This operation outputs a specific probability. As we see in this chart, it assigns a number between 0 and 1 for each classification label the model is trying to predict. Right alongside this is the activation layer. In modern architectures, a function called ReLU is the default choice for this step. Look at how ReLU behaves on this graph. It passes any positive value through completely unchanged, but it strictly clamps all negative values to 0. This introduces a necessary nonlinearity into the system. Without it, the network would only calculate linear functions, making it unable to parse the complex, variable data found in actual images. Now we come to the core engine of the CNN, the convolutional layer. Unlike the multi-layer perceptron, which requires you to flatten an image into a 1D vector, convolutional layers operate directly on 2D and 3D data. The input to this layer is usually a 3D matrix. It has a spatial resolution defined by its width and height, and a depth defined by its number of channels. To process this block, the layer uses small filters, or kernels, usually sized 3 by 3 or 5 by 5. The spatial resolution of the filter is small, but it matches the exact channel depth of the input layer beneath it. We place the filter over the input, multiply the overlapping elements, and sum the results. This single calculation produces one output value for the new feature map. We then slide the filter across the image. The distance we move the filter is called the stride. If we increase the stride, say to 3, the kernel moves further with each step, which directly shrinks the size of the resulting output map. Because continuous convolutions shrink the resolution, we apply padding. We wrap the outer edge of the input with 0-valued rows and columns. This prevents aggressive shrinking and retains the data at the borders of the image. We can calculate the exact size of the final output map with this formula. The new size equals the input size plus 2 times the padding minus the kernel size divided by the stride plus 1. By tuning the kernel sizes, strides, and padding, we extract visual features while maintaining strict control over the network's spatial dimensions. There is a limitation to convolutional outputs. They are highly dependent on the precise position of a feature.
A tiny movement in the input image can completely alter the resulting feature map. To address this, we use a pooling layer. Its function is to intentionally downsample the image, creating a lower resolution version that keeps important structural elements while suppressing minor noise. There are 2 main ways to pool data. Max pooling, shown here, evaluates a patch of the feature map and extracts only the largest value, discarding the rest. Alternatively, average pooling evaluates the same patch and calculates the mean value of all the pixels within it. By progressively shrinking the spatial representation, pooling layers decrease the total amount of parameters. This filters out exact positional variance and reduces the network's overall computational load. Introduced in 2015, the batch normalization layer quickly became standard practice because it stabilizes the training process and helps models converge faster. Here is what it does to the data. It selects a channel and calculates the mean and standard deviation over a small batch of images. It then normalizes that data, snapping it into a clean, zero-mean-centered bell curve with unit variance. However, forcing this strict normalization can sometimes hurt the training process and increase the model's error rate. To fix this, the authors added 2 learnable parameters: a scale parameter called gamma, and a shift parameter called beta. Gamma and beta give the network an escape hatch. If normalization is hurting the loss, the network adjusts these sliders to simulate an identity operation, effectively reversing the normalization process and returning the data to its original state. There is an ongoing debate regarding placement. The original paper recommended placing batch norm immediately after the convolution and before the ReLU activation. However, many modern implementations apply ReLU first and batch norm second. The best approach is to test both for your specific problem.
Regardless of sequence, batch normalization is a fixture in modern models. It mitigates issues with activation functions, provides training stability, and acts as a powerful regularizer against overfitting. Before we put it all together, we need to understand the concept of the receptive field. This is the specific region in the original input image that affects a single pixel in a given feature map. In the very first layer of our network, a single output pixel only contains information about a tiny local neighborhood, like a 3x3 square on this input image. But as the network stacks deeper layers, applying continuous convolutions and pooling operations, the receptive field grows. A single pixel in a deep layer traces its inputs expanding backward, allowing it to see a massive chunk of the original image. A larger receptive field allows deep layers to integrate broad contextual relationships and abstract meanings rather than isolated edges. Step by step, we have assembled the pipeline. We take BRE-D image data, process it through convolutional filters, apply batch normalization, clamp it with ReLU activation, and condense it with pooling before a fully connected layer delivers the final prediction. Next week, we will examine the dropout layer, another essential component for regularization and building redundancy. But for now, you possess the complete structural blueprint required to understand and build modern computer vision models.